In this video, we are going to be learning how to predict whether a substance is soluble in water based on what type of compound it is. How can you tell if a compound is soluble? The method we use depends on what type of compound it is. Acids are always soluble in water. Both strong acids and weak acids form aqueous solutions, so they are written with the state symbol AQ when dissolved in water. For molecular compounds and ionic compounds, the answer is not as straightforward. Some dissolve readily in water while others do not. For molecular compounds, we will use the principle like dissolves like, which depends on the molecular polarity. For ionic compounds, we will use solubility rules found on your reference sheet. Before we can determine whether a molecular compound is soluble, let's review molecular polarity. A molecule is polar if it meets two requirements. First, it must contain at least one polar covalent bond. Second, it must have an asymmetrical molecular shape, so the dipole moments do not cancel. Features that make a molecule asymmetrical include lone pairs on the central atom or different terminal atoms bonded to the central atom. Nonpolar molecules are symmetrical. A useful shortcut is that any molecule made out of only carbon and hydrogen atoms is nonpolar. When predicting whether two molecular substances will dissolve in one another, we use the general rule like dissolves like. Polar solutes tend to dissolve in polar solvents, while nonpolar solutes tend to dissolve in nonpolar solvents. If one substance is polar and the other is nonpolar, they generally do not mix. A familiar example is oil in water. Oil contains mostly carbon and hydrogen atoms, making it nonpolar. Water is polar. Water molecules are capable of forming strong hydrogen bonds with one another, while they can interact with oil only through weak dispersion forces. Because hydrogen bonding is much stronger than dispersion forces, water is much more strongly attracted to itself than it is the oil. As a result, the oil separates instead of dissolving. Now let's consider these two molecules shown here, dimethyl ether and water. What intermolecular forces can exist between these two substances? Will dimethyl ether dissolve in water? First, determine whether each molecule is polar. Water contains polar oxygen-hydrogen bonds, and it has two lone pairs on the oxygen to give the molecule a bent asymmetrical shape. Therefore, water is polar. Dimethyl ether also contains polar carbon-oxygen bonds. The oxygen atom has two lone pairs, giving the molecule a bent geometry around the oxygen atom. Therefore, dimethyl ether is also polar. Since both substances are polar, dimethyl ether is soluble in water. Now let's identify the intermolecular forces. First, dispersion forces are present. Dispersion forces are present between all molecules. Second, because both molecules are polar, they experience dipole-dipole forces. Finally, can they hydrogen bond? Hydrogen bonding requires one molecule to have a hydrogen directly bonded to a nitrogen, oxygen, or fluorine, the hydrogen bond donor, while the other molecule must have a lone pair on nitrogen, oxygen, or fluorine, the hydrogen bond acceptor. Water can act as the hydrogen bond donor because it has hydrogen atoms bonded to oxygen. Dimethyl ether has lone pairs of electrons on its oxygen atom, allowing it to act as the hydrogen bond acceptor. Therefore, water and dimethyl ether can hydrogen bond to one another. Notice something interesting. Water can hydrogen bond to other water molecules and to dimethyl ether. However, dimethyl ether cannot hydrogen bond to itself because it has no hydrogen atoms directly bonded to oxygen. Here's a practice problem. Determine whether each compound is soluble in water. Remember that water is a polar solvent, so polar solutes tend to dissolve according to the principle like dissolves like. Our first compound is formaldehyde. The carbon-oxygen bond is polar, and the atoms around the carbon are not the same element. This gives the molecule an asymmetrical distribution of charge. Formaldehyde is a polar molecule, so it will be soluble in water. Next is ammonia, NH3. The nitrogen-hydrogen bonds are polar, and the lone pair on the nitrogen makes the molecule asymmetrical. Ammonia is polar, and so it is soluble in water. Our next compound is propane. Notice that propane contains only carbon and hydrogen atoms. Any molecule made up of only carbon and hydrogen is nonpolar. Since propane is nonpolar, it is insoluble in water. Finally, we have hydrochloric acid. Remember that all acids are soluble in water. Hydrochloric acid is a strong acid, so once dissolved, it actually completely ionizes into separate hydrogen and chloride ions. Now let's consider ionic compounds. The ions that make up ionic compounds carry full positive and negative charges. These charged ions can form strong ion-dipole attractions with polar water molecules. However, not all ionic compounds are soluble. For some ionic compounds, the attractive forces between positive and negative ions are stronger than the attractions between ions and the water molecules. Those compounds remain largely undissolved. As a result, some ionic compounds are soluble, while others are insoluble. When a soluble ionic compound dissolves, it separates into its cations and anions and primarily exists in an aqueous solution. An insoluble ionic compound remains primarily a solid precipitate at the bottom of the container. To predict the solubility of ionic compounds, use the solubility rules located on your reference sheet. The reference sheet contains two tables. The first table lists ions that are generally soluble. The second column in each table lists any exceptions. For example, chlorides are generally soluble, but silver chloride and lead chloride are exceptions, and those are considered insoluble. The second table lists ions that are generally insoluble, along with their exceptions. For example, carbonates are generally insoluble, but sodium carbonate is soluble because sodium is an exception. Notice a trend. Many of the ions in the soluble table have charges of +1 or -1, while many of the ions in the insoluble table have charges of 2 or greater. Higher charges create stronger electrostatic attractions between ions, making those compounds more likely to be insoluble. However, whenever possible, follow the solubility rules on your reference sheet rather than relying on trends. Here's a practice problem. Use the solubility rules on your reference sheet to determine whether each ionic compound is soluble in water. Then decide whether it primarily exists as an aqueous solution or as a solid. Our first compound is potassium hydroxide, KOH. Hydroxides are generally insoluble, except when paired with group 1 metals. Since potassium is a group 1 metal, potassium hydroxide is soluble and primarily exists as an aqueous solution. Next is silver bromide. Bromides are generally insoluble, but silver is an exception. Therefore, silver bromide is insoluble and primarily exists as a solid. Next is calcium chloride. Chlorides are generally soluble, and calcium is not an exception. Therefore, calcium chloride is soluble and primarily exists as an aqueous solution. Next is lead-2 nitrate. All nitrates are soluble, with no exceptions. Therefore, lead-2 nitrate is soluble and exists primarily as an aqueous solution. Finally, we have lead-2 sulfate. Sulfates are generally soluble, but lead-2 plus is an exception. Therefore, lead-2 sulfate is insoluble and primarily exists as a solid precipitate.